Welcome back. What better way to start this session than with the Imperial March? This is the last session of our virtual mini conference. I'm Marco Santander. I'm assistant professor at the University of Alabama. And I'm pleased to introduce Dr. Kristina Nyland. Dr. Nyland is a National Research Council postdoctoral fellow at the Naval Research Laboratory, where she studies topics related to the formation and evolution of galaxies and supermassive black holes. So welcome, Kristina. I'll give you a 4-minute warning, and please take it away.
Thank you very much, Marcos. And thank you to everyone for tuning back in, okay? So I think the speakers earlier in the previous session did a fantastic job of introducing the topic of active galactic nuclei. So I'll start by just adding to that. AGN are among the most energetic objects in the universe, and they can at times outshine entire galaxies by orders of magnitude. Now, a subset of AGN are known as radio loud, and these sources are able to launch large-scale jets of relativistic electrons that may extend well beyond their host galaxies. In addition, AGN jets may heat, disrupt, or expel material along their paths, potentially leading to galaxy-scale feedback capable of altering star formation conditions, and this makes active galactic nuclei important for galaxy evolution. Right, as interesting as large-scale AGN jets are, we've known for decades now that a significant fraction of them actually have compact sub-galactic jets. And some examples of such sources are highlighted in this figure from a long baseline radio survey called Mojave that monitors the brightest known compact jets on milliarc-second scales. Now, the origin of compact jets may arise from projection effects, as is the case for blazars, which are AGN with jets pointed directly at us. Jet compactness can also arise from physical effects, such as jet youth or confinement by a dense ISM. Now, in any case, compact AGN are inherently tricky to study because of their small intrinsic sizes that require high angular resolution. And because of this, there are still a lot of fundamental open questions. For instance, we still don't understand the life cycles of compact jets. We don't really know their dependence on redshift. We don't know what kinds of galaxies they all necessarily live in. And the topic that I'll be focusing most on here is the role of compact jets in jet ISM feedback and how we can make progress in that area. Now, one approach to identifying compact jets is through multi-epoch radio surveys, such as the Very Large Array Sky Survey, or VLASS. So VLASS is a large survey of the entire northern sky above a declination of -40 degrees. And it's actually the third large survey being conducted by NRAO with the Very Large Array above a gigahertz, following in the footsteps of NVSS and FIRST at lower resolution. And I have an example in the lower left of this slide showing a comparison of the exact same source observed in all three surveys. Now, unlike NVSS and FIRST, which were observed in a single epoch and at 1.4 gigahertz, VLASS is being carried out at 3 gigahertz over the course of 3 distinct epochs. And the first epoch of VLASS, at least in terms of the observations, has actually been completed. And you can learn more about the preliminary survey data products in Lacey et al. 2020. So with the goal of identifying known AGN with potentially a new onset of radioactivity on decades-long timescales that could be related to compact jets, we've begun searching for transients between FIRST and VLASS Epoch 1. Now, there are about 600,000 sources in the 10,000 square degrees of overlap between these two surveys. And what's more interesting is that there are actually thousands of sources detected in VLASS that are not detected in FIRST. And these sources are a mix of slow radio transients like tidal disruption events, which we heard about from Kate Alexander, and also intrinsically variable radio sources such as AGN. And I'll be focusing on that latter population of AGN that are variable in the radio in the remainder of this talk. So far, our search for radio transients, it covers over 3,400 square degrees of VLASS Epoch 1. And that's highlighted in this figure by the dark orange tiles. And out of 2,000 candidates that were selected through heroic human vetting efforts, now we found 167 sources above a millijansky within an arcsecond of an optical or infrared AGN based on SDSS or WISE. Now we further pared down the sample by requiring VLASS fluxes to be above 3 millijanskys. And the goal of that was to rule out steady but optically thick sources. And this gave us a sample of 26 newly radio loud AGN. Here's a comparison of first and VLASS cutouts for a few of our sources, and it clearly highlights the lack of a detection in first in the clear presence of a compact radio source 2 decades later in VLASS. And I'd like to emphasize that the sensitivities of first in VLASS Epoch 1, they're comparable, so this is not a sensitivity issue. So the gist of it is our sources were radio quiet quasars in first, and then 20 years later, VLASS has revealed that they are now radio loud. So these are powerful AGN changing on human timescales, which goes a little bit against our common perceptions of how radio AGN behave. Now again, these are a few optical images and spectra from SDSS. I'd just like to highlight that about half of our sources are in fact type 1 broadline quasars, so these are very powerful objects. So let's talk a little bit more about radio variability amplitudes and timescales. So first, I'll remind you that typical radio AGN variability is usually at the few tenths of a % level. AGN typically, it's more like a flickering rather than a switching on. Now here you can see in the left-hand plot especially, we're dealing with something a bit more extreme in many cases. So we've seen sources brighten by 100% to over 2,500% at 1.5 gigahertz over a couple of decades. Now on shorter timescales, is shown in the plot on the right, we find relatively steady fluxes at 3 gigahertz on timescales of months. And so overall, these properties support intrinsic radio AGN variability as opposed to something like propagation effects from scintillation. So here I've listed some plausible explanations for the intrinsic radio AGN variability. And I don't have time to really cover these in detail, but plausibly you could have AGN flaring. And this might be associated with stochastic supermassive black hole accretion or shock propagation along the jet. You could also have jet reorientation. And Sarah Brooks-Villar spoke to this a little bit in her talk. You could actually have a supermassive black hole binary orbital motion that could affect the line of sight angle between us and a jet that could cause radio variability. And the third possibility is newborn jets. And so in this case, you would actually have AGN that launched jets just in the last few decades. And in the limited time that I have, I'll be focusing on this last scenario of newborn jets, since it does currently fit the data quite well. So one way of investigating the newborn jet scenario is to determine the radio SED or spectral energy distribution shape. And this gives you insights on the conditions of the relativistic electrons, and you can make some connections to the evolutionary stage. So on the left here, just as a reminder of a typical optically thin radio SED for a lobe-dominated large-scale galaxy, you can see it's described by a simple power law. And that really contrasts with the plot on the right, which is the radio SED for a young and compact AGN. And as you can see, it has sort of this peaked shape here. And peak spectrum sources, like young and compact radio AGN, are really well suited for higher frequency radio surveys like VLASS. So here's some real data from our quasi-simultaneous multiband VLA follow-up from 1 to 18 gigahertz. And the key takeaway here is that simple power law models don't fit the data. You really need to have a curved radio SED model to fit the data points. And all of our sources that we followed up, there are 14 in total, they all have radio SEDs that look very much like this. And this is consistent with what we would expect in the case of young, possibly newborn compact jets. So the peak or turnover frequencies from the radio SED data that I just showed, they can actually help constrain source sizes, and then you can do rough estimates of ages. And so I've shown here a tool called the turnover size relation. And I've plotted our sources here. They're all upper limits in terms of their sizes in our highest resolution VLA follow-up at 0.1 arcsecond resolution. So the magenta points are limits with redshifts, and the rainbow colored arcs are for sources that lack redshifts. And we're just showing the full parameter space of size upper limits. So overall, the VLA finds sub-kiloparsec scale jets that if we assume they were to lie on this relation, if we could get high enough angular resolution data, could have ages as young as a few decades. We can also place our sources in the context of the overall radio population using the luminosity size diagram shown here. So this diagram tracks the evolution of radio AGN through different life stages, from parsecs all the way up to hundreds of kiloparsecs. Now our sources are shown by the magenta upper limits here, and again, rainbow arcs for sources with no redshifts. And we find that their sizes and luminosities are consistent with the population of young radio AGN, such as gigahertz peak spectrum or GPS sources. And that's highlighted by the green shaded region on this diagram.
Sorry, 4 minutes.
Now, what will happen to our sources in the future? So they may continue brightening until they reach kiloparsec scales over hundreds or maybe thousands of years. And then they may eventually, over timescales of millions of years, become large-scale radio galaxies. However, if their central engines are suddenly cut off, they would instead rapidly fade away on relatively short timescales. Now, we're currently working on constraining the demographics of this population in VLASS to better understand how compact jets evolve and really quantify their potential impact on galaxy evolution through jet ISM feedback. And the idea here is that if short-lived radio compact AGN jets are more common than we thought, and there are a lot of them at high redshift, that would mean that there's a great potential there for jet ISM feedback, and we need to investigate that further to really understand how it impacts galaxy evolution. So looking towards the future, we're monitoring our candidate newborn jets, and we aim to ultimately construct a larger statistical sample as VLASS progresses. On the multi-messenger side, I hope there will continue to be new opportunities for understanding AGN jet formation, physics, and feedback, combining electromagnetic observations with data from other messengers. And so some of these additional messengers include things like gravitational waves, primarily from pulsar timing arrays that are sensitive to supermassive black hole mergers. Sarah talked a bit about this in her presentation. You could potentially have a supermassive black hole binary that could then exhibit variable radio emission through jet disruption or reorientation, or perhaps even formation in a circumbinary accretion disk. It's also possible that jet ISM feedback from non-merging supermassive black holes could lead to particle acceleration that might even produce gamma rays or neutrinos. And in fact, while I was preparing for this talk, I learned about a recent Fermi detection of a young non-blazar radio AGN that was just published a few weeks ago by Lister et al. And I've shown a picture of that source in the center of the slide. And finally, in the 2030s, there are exciting prospects for high-resolution imaging with the next generation very large array, which I think we've heard about a couple of times now in different talks. I just want to highlight that the main design of NGVLA has baselines in the American Southwest going out to about 1,000 kilometers. But there's a possibility of including additional stations out to longer baselines, out to thousands of kilometers, 9,000 kilometers almost. And if we include that in the design, we would be able to achieve sub-parsec scale imaging at redshift 2 in the highest frequency band. And this would be a game changer for understanding compact jets and their role in galaxy evolution. So I think my time is probably just about up here. Hopefully I've convinced you that this is an exciting era to be studying young and compact AGN jets. And I'll just leave you with the final takeaway message that radio AGN jets, they're not as constant as we often think of them to be. Radio quiet AGN can become radio loud on human timescales. And it's really important to use dynamic radio surveys to catch young jets, and then also high resolution observations in the future. So thanks for your attention, and that's all.
Thank you very much, Kristina. Very nice presentation. And let me take at least one question from the chat window. There are several that are interesting, but I hope that people can also join the Zoom discussion afterwards. So from Demos Casanas, there's a From the pictures I've seen, jets pass only through a tiny fraction of the volume of the galaxy, and he doesn't see how they, one can claim that they influence the evolution of the galaxy itself. So can you comment on that for feedback of AGN jets?
Right. So our understanding of jet-driven feedback is we have a good understanding at lower redshifts, understanding how large-scale jets interact with the intercluster medium and intergalactic medium. And they heat gas there and they prevent it from cooling to form stars. But when you have compact jets, they do interact. We know that they do interact with the ISM. And at high redshifts, a lot of that ISM, a lot of the raw star formation material might be more concentrated in them. And so through either expelling the gas or heating it to make it less able to efficiently form stars, you might actually be able to at least affect star formation like within the disk of the galaxy. And if it happens commonly with a short duty cycle, those effects could multiply over time.
Well, thank you very much. And let's take the rest to the discussion Zoom sessions.